A lot more people than there's supposed to be. That's okay. Okay, so first things first, there's a lot of you. There's definitely more than 60 of you, and there's one of me. So you can't be talking a lot. I know it's like your neighbor, but whenever I talk to your neighbor, it's really loud and really distracting. So make sure you're quiet. If you have a question, ask me, because that's the whole point. The other thing is, we have to keep it down, because there's other classes going on, because we're in another classroom now. On that note, there's a class before us. I think it's a German class, or there's some class before us. You can't go into the class before this to get a seat, because it's not your class, and it's really destructive and rude to the professor and to the students. And if you're waiting outside, you have to keep your voices down, because it's also really destructive. So that can't happen again, okay? You have to wait outside. We don't have the room until, if their class ends, we shouldn't have the room until like 10 or 15 minutes before. So no one should be in here from this until then, until their class is completely over and their professor has dismissed them. So make sure you guys aren't going in there and causing disruptions, because then we won't get this room anymore, and then we won't have reviews anymore, because I won't have a room to do them in. So don't do that if you want to continue having reviews, and make sure you're respectful of the other classes that are going on, because there's so many of us. Okay? So we don't want to lose our review room. That would be very bad. Okay? So we'll start at 7:30. And obviously there's a lot of people, I understand you want to get a seat to see, but you can't disrupt the other class. Okay. So let's begin. I had a few random people write on the board. I wrote down some topics, some words, because sometimes there are words and people think they know the word, and I think you know the word, but I don't, it's not right. So I don't know who wrote what, so I'm not personally attacking you if you feel that way. So I have conjugated, aromatic, electron withdrawing, and donating groups, and activating and deactivating. So they're just terms that we've been using a lot lately, which you need to know. So for conjugated, if you can't read, we have system pi electrons going throughout the compound, resonance, alternating single and double bonds, they're stable, all good. So yeah, when I think conjugated, I think of something like this, where every other is a double bond. So resonance also, because they're stable through resonance. I think you can see that in the film. Conjugated also, we know is stable, and we know we want to keep things conjugated if we can, and it also goes along the lines of aromatic, because we know we go through aromaticity, we go through whether or not it's conjugated when we're talking about aromaticity. So here we have the dreaded 4n plus 2 rule. We have side-to-side overlapping pi orbitals. Aromatic compounds are stable, so it's true. They're also conjugated, stable. Anti-aromatic, non-aromatic, someone's favorite word is aromaticity. Awesome. And sp2 hybridized. So this is all good things that I'm seeing. Withdrawing and donating, we have diene and dienophile, which is from Diels-Alder. We have ortho, para, and meta directors. We have that methyl groups are donating, good. Got some pictures, and we have the halogens are confusing, okay. And along the same lines, activating and deactivating. So all of this looks good, so there's nothing that I'm completely concerned about. So I'm going to start with Diels-Alder, but I'm going to go through it quickly because it's already on the internet. And then go into aromaticity, and then do chapter 15. Well, most of chapter 15. So make sure you can do these questions, because you should really be mostly familiar with Diels-Alder right now. And I want to make sure we have plenty of time for chapter 15, which is the new stuff, which is a lot of synthesis stuff. But it's good because they're really easy synthesis stuff. Much easier than the other ones you've been seeing, because there's really only one way to go through them. So I want to make sure we get to that, because you're pretty much definitely going to have that. Okay. Can everyone hear me? Can anyone not hear me? Cool. Okay, so Diels-Alder, which is basically the first thing you're responsible for. I killed my marker.
Sorry.
What did you do? Like stab the head. Alright. So, when we're doing Diels-Alder, we're basically taking two pieces and putting them together, which is most of organic chemistry. So, our two pieces, we have a piece that looks like this, which has two double bonds. We have a piece that looks like this, which has one double bond. Two double bonds. And this guy likes double bonds. That's an H. Alright, so generic Diels-Alder mechanism. Again, mechanism, same thing every single time, over and over and over again. Sometimes the pictures look different. The stuff that you're drawing the arrows from look different, but you always draw the same arrows. Should have seen that last semester. All your mechanism is exactly the same as long as you're doing the same reaction. Diels-Alder mechanism isn't any different. There's two ways to draw it. Draw out the actual mechanism, but they're both acceptable. So you can either, the way in the textbook is like this, which I think looks really weird and I don't like to draw it that way. I draw it like this. It means the same thing. I just don't like those arrows. So either one, whichever one you draw is acceptable. Just make sure you draw it the same way. And if you look, either one, you're going to take your extra pi electrons, you're going to form a bond. Forces these extra pi electrons away, and they're going to form a bond here. These are just very far apart. Forces these pi electrons away, but if you notice, when this guy leaves, he's missing, so he just fills them in here. So we should always get something like that. You do that every single time. Sometimes there's stuff hanging out to the side. It doesn't matter. It doesn't make a difference. It doesn't make a difference with your arrows. So either one, whichever way you draw it is fine. And these are just like the smallest pieces that you can have to put together. So we're good with the mechanism, and we know that this and this is the new bond being formed. And the last arrow is always the double bond in our product. Okay. So far away. Alright. So, when we're putting these two pieces together, there's a few things we have to make sure with stereochem, regiochem, all this stuff. We want to always draw the diene in this sort of cis conformation, meaning if your piece looks like this, just redraw it like that. That's it. Just redraw it. Then do your arrows. Okay? This conformation is easier for the pieces to go together, because if you look, so if we have something like this, we just turned it. Yeah, it's, what is it, C something? S, cis. So, does that make sense? It's with reference to this double bond.
Okay, that's what I'm
Yeah. Yeah. So anyway, this guy, he's locked in that position. So this one will be spitting, so sometimes he is, sometimes he's not. This guy's locked in it, so things like that are good. You don't really want bulky groups, like really bulky groups, pushed in here, because that's where you want your mechanism to go through. The other thing we can do is to make our two separate pieces more reactive, we can add things onto them, which is our withdrawing or our donating groups. You always want your withdrawing on your dienophile, and your donating on your diene. Alright? So, if we look, let's do this first. So, if we have a group on our diene, okay, we want to keep the stereochem, we want to preserve the stereochem within this piece, and we want to preserve the stereochem within this piece. So let's say we have one here that's like this, A and B, whatever it is. When we go and draw our product, these guys are trans to each other, yeah? So we want to draw them in our product with trans stereochem. So you want to make sure you preserve that. Same thing with the diene. Let's look. keep in mind when you're putting your pieces together is how you line them up to put them together. So if we look, I have the biggest whiteboard in all the way. If we look something like this. Okay, we have a donating group and a withdrawing group, whatever they are. If we fill in charges, we'll double it. We'll have a plus there and a minus on this side because it's withdrawing. And we'll have the opposite here. And if you look, we're good with the whole plus and minus subtract, right? If you look, they match up as plus and minus. So plus and minus will attract, they'll go together nicely. If we do it like this, and we move the donating group, so we went from being on the edge to being in the middle, and we draw those charges in, just from withdrawing and donating, pulling and pushing electrons. Again, plus and minus line up, those pieces are good. Last one, if we line them up like this, and put these charges in, based on the location of the donating and withdrawing groups, your pluses and minuses don't match up as opposites, they match up as pairs. So we know those pieces don't want to go together like that. So if you notice, these ones are, if you number 1, 2 to each other, when we make the product, these guys should be 1, 2, 3, 4 to each other, and these guys are, what's it, 2? 1, 2, 3 to each other. So 1, 2, 1, 4 is good. I mean, you can draw out your charges every time, but it's always going to look like this, basically, generically. So 1, 2, and 1, 4, your charges are going to match up correctly. 1, 3, they're not. So if you're in a situation where you have something like this, take one of your pieces and flip it down, or flip it completely upside down, the whole thing. So then if we look at these two, the new one, they are 1, 2, 3, 4 to each other. So if you take your 1, 3 piece and you flip them upside down, he'll line up correctly. Just make sure you're counting right. So if you look at the charges, you'll know which piece, how you want them to go together in reference to the groups. All right. Okay, let's do. Okay. Any questions with that? That should be good because you already did a workshop on that. No questions. All right, so if we look at a problem, let's do this really basic one. Okay, so I have my 2 pieces. Okay, dienophile. Dienophile has a withdrawing group on it, so that's good. That'll make it more reactive. We want to take the diene, we want to redraw it, and we want to line up so it looks like our generic piece. Okay? After we do that, we want to make sure we redraw it correctly. So these guys are trans to each other. So I'm going to draw this guy here and this guy here. Draw the exact same mechanism every time. Redraw the product. That. We have the methyl on this carbon. And the carbonyl on that carbon. Only thing we have to consider is the stereochem. Here, they're trans to each other. They're on opposite sides, so when we draw them, we want them to be trans to each other. Makes sense? Just preserving the stereochem. In this case, we didn't have any groups on our diene, so we didn't have to worry about 1, 2, 1, 4, 1, 3. But other than that, it's pretty cool. Another thing, one on your task? I mean, not on your task, on your workshop. This one? We know we're going to draw the same arrows, right? Every single time. And we know we're just going to take pi electrons and make a bond, and then take pi electrons and then make a bond, and then take pi electrons and make a bond. That's all we're doing. So when I go to do this problem, and I redraw it, okay? I'm still drawing the same arrows. Everything works. Pi electrons, make a bond. Pi electrons, make a bond. Pi electrons, make a bond. Just because I have a triple bond and I have extra pi electrons, it doesn't matter. I also have methyls and other nonsense going on, but if they're not in the mechanism, then you just keep them. If you didn't touch their bonds, you just keep them. So this guy, I didn't use him in the mechanism, so when I draw my product, I'm just going to draw him again. So your extra bonds here, you just redraw. So you have the double bond that you formed in your normal Diels-Alder mechanism, and you have this double bond left over because you didn't use it. Then we have a methyl here, a methyl here, CO2CH3, CO2CH3. And remember, there's no wedges and dashes on double bonds. Or planar. Those carbons are planar, so there's no wedges and dashes. So these guys didn't have stereochem here, and they don't have wedges and dashes there either. And then the last part, all we need to do is look at our methyls and see that they're in opposite positions to each other. If you look all the colors. This guy is in a C position. And that guy's in a T position. So we know that they're opposite, so when we redraw them, we want them to be opposite. Okay. As far as this goes, it's kind of hard to see for some people. If I have a diene, right? In reference to the center bond, the single bond, this is cis, right? Same thing on the bottom. And that's trans. Does everyone see why? It's in reference to the center bond. So people get kind of confused why that position is cis. So you have a cis position there, a cis position there, trans, and trans. And the ones in the middle are N. They don't like that. Does everyone see those ones, those groups?
Wait.
Yeah. Let me write somewhere where I'm not so short. Okay, diene. If we look at this center bond, okay? If I drew a bond cis to that center bond, it would be there. Right? Because cis double bond looks like this. So it's that same shape. If I look at it, I don't really know. With reference to the center bond, and I draw a bond trans to it, it looks like that. Just because it's in the trans position. And it's the same thing on the bottom half. So the group, whatever group that's on this bond in that position is a C group. The ones on the green ones are T groups, because they're in the T position. Okay? So for this one methyl was in the T position, one methyl was in the C position, so I know they're opposite. So in my product, I do them opposite. Okay.
For when you did the stereochem for the methyls,
Mhm.
like you did the trans,
Mhm.
could you have done the other way too? Like
Could have flip-flopped them? Yeah, same thing. So you could have drawn the same thing, but as long as they're trans
Right.
to each other, that is the best by drawing. Good with the stereochem so far? Diels-Alder is like, can you draw 3 arrows and keep track of all the stereochem and redo them? Alright. Okay. Let's do while we're on it. So, triple bonds is the same thing, and you have an extra double bond at the end because you didn't use it, it's left over. So if I like plucked it off here and did my question, and then I just put it back. So you're not using it, you just redraw it. So they're really no different than regular problems. The only other ones that are kind of weird are the intramolecular. That's because they're difficult to approach. And there's one methyl. Okay, so when I have intramolecular, the way I do them is I look at it and I say, I know I want to do this, because that's all I do for Diels-Alder. So I look at this and I say, how can I make it look easy, like that? So I say, all right, this is my diene, and this is my dienophile, and there's some stuff in the middle, but it's really not that important. So I'm going to take just this piece, and I'm just going to redraw it in the right confirmation to see if they're drawing. Okay? Let me number these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So here I have 1, 2, 3, 4. And then I take my dienophile piece. That's carbons 8 and 9. And before I draw it, so I don't have to erase it, I see I have one group here on my diene, one group on my dienophile. So I have a group on both pieces. So I know I want to make their charges line up, so I know I want them to be either 1, 2 or 1, 4. So if I were to draw my carbonyl on this carbon, they would be 1, 2, 3 to each other. So instead of drawing it and redrawing it, I know I can do 1, 2, 3, 4. So I'm just going to draw them over here. Okay? If you draw it, if you don't see it and you draw it and then you count and they're 1, 3, just erase it and draw it upside down. Or save time and do it once. Whatever works. So now I have my pieces. Let me number these. 9 has the carbonyl, so he's 9 and he's 8. Same mechanism. He's my methyl. He doesn't get stereochem because he's still on a double bond. And I have him over here. So everyone's good with just this. Does anyone not see that? Okay. So if I look here, this is 8 and this is 9. Right? So right now I have 1, 2, 3, 4, 8, 9. But you know, we're missing carbons. We're missing carbons 5, 6, and 7. But conveniently enough, those go between carbons 4 and 8. So I go 4, 5, 6, 7, 8. You could also do that alternatively here. Once you redraw them nicely next to each other, you could go 4, 5, 6, 7, 8, and done the exact same thing, but then I only have to draw it once. So I do it at the end. Okay? So just take the pieces you need and do that, and then add the other ones. So as long as you number your carbons correctly, you just have to fill them in with the right number. So here I have 5 mercury because I know I needed to put 3 carbons in. And you can write numbers on your carbons, it's not a. Then last thing I need to check is my stereochem. He doesn't get stereochem because he's on a double bond. These guys I know I want to be the same stereochem. The only thing we have left is to see this stereochem in reference to this guy. So, I'm teaching them endo, Peter. Close your ears if you want to. We're doing endo. He doesn't teach. The teacher's not telling you. We're doing endo. So for the endo product, you want whatever group is in your C position to have trans stereochem to your electron withdrawing group. And keep in mind, your C and your T group are always on your diene. And your electron withdrawing group should be on your dienophile. So these are talking about the 2 separate pieces. Okay, so keep track of where your C group is and where your T group is. And the other way to say the exact same thing, but from the opposite side, would be that your T group is going to be cis to your electron withdrawing. Oh, this should be not trans. This should say empty. Alright. Okay. So if we look here, this side, it kind of doesn't look like we have groups, but we do. So if we look here, oh, I probably should have picked a different color. If we look in T with reference to that, we don't have it. But if we look, see if I can draw this better for you. Not really. Oh, look here. So this is the center bond, right? This guy. Does everyone see that's a T group? Does everyone see that it's in the trans Z lines? Is anyone gonna answer?
Yes.
Okay. So we know that that's a T group. So 4 to 5 is a T group. We want our T group to have the same stereochem as withdrawn. So I'm going to pick a stereochem for him, because I can. And I know I'm on my 4, 5, which is my T group, to have the same stereochem. So I do this, you know it's ugly. Then I know this is a ring, so I want him to be the same way. And the way to draw that a lot prettier, to leave that, and give the stereochem to your H's, just because it looks prettier, but it doesn't matter. Because if they're dashed, then the needs to be wedged. Does everyone see why that's a T group?
Yes.
The T group part? Yeah. So if you look in the starting part, when it was drawn straight, our C and our T group are in reference to this bond, at the center of the diene. So if I look at my bond and my center of my diene, on the left side I don't have any groups. On the right side I have the rest of the molecule, the rest of the chain. So in reference to the center bond, it's in the trans position. It's trans to that center bond. So this is in the trans position. This would be the C position, but there's no group there. So the 4, 5 bond is in the T position. So when I'm redrawing my product, whatever group is in the T position has to be cis to withdrawing. And I know that my carbonyl is withdrawing. So I just picked a stereochem for that, and then I gave my T group the same stereochem. Yes? Yes? Yes. Okay. 2 people know how to do the question. Good deal. All right. There are no questions. I erased it. Thank you so much. So same thing. Again, intermolecular is the same exact thing. It's just a little tricky to draw. So that's the trick I use, so I don't mess up the drawing. Okay. Let's do the only other kind of thing that feels all there. Just going backwards. So they give you the product, and you want to go backwards and figure out what pieces you're starting from. Okay? So feels all there. Let's look. How many colors can I use? Endo's more favorable. So we were taught to always draw the endo product, but he's not teaching you it. But I can do it anyway. So yeah. Exo is just like flip flop. Yeah, but endo is more stable. More favorable. Alright, so this is like one of those games you have to keep track of the coin under the hat. This center bond, don't look away. Very important. And this guy is important. And even other. Alright. Oh, I'll send somebody. Okay. Mechanism. This goes to product like this. Right? Alright. So this center bond, if I personally knew those carbons, they are here. Yes? These guys are here. Yes?
Yes.
These new bonds that I formed, not this guy, not the double bond, the 2 new bonds are here and here. That's just following the mechanism through. Keeping track of your electrons with pretty colors. Yes, okay, good. So if I were to take this, I'm just going to redraw out all the circles, and deconstruct it. I know that this double bond used to be the center of my diene, so the red guy. And I know directly across from him was my dienophile, which is the orange guy. And I also know that the two bonds connecting the orange guy were newly formed bonds. So going backwards, I know that these bonds used to not exist. So I'm going to pretend they're not there. So if I erase those guys, because they weren't there to start, because I know that they're these newly formed bonds, I know that my arrow will always point to my dienophile, which I know is the double bond. And I know that it always starts from the center of my diene. So I flip it to look like a diene. So where it points, you make it back into a double bond. And where it came from, you make the center of the diene. And the two bonds next door are always going to be these blue bonds. So you know to start, they weren't there. So you just ignore them and erase them and they can go away. So if we look again, this is my red guy, this is my orange guy, and these were my blue guys. So if you keep track of them that way, you know where your pieces break, because I know that the blue bonds will always be the same place because I'm always drawing the same arrows. So going backwards, I know I can always undo them the same way to get my pieces. So let me get these colors again. Red, okay. So this is my red guy. Okay, so I always find my newly formed double bond, because I know that the last arrow mechanism will always put the double bond in the center of the diene. So I find him. Then I can do the problem. I know that directly, where's my guy? Directly across is going to be my dienophile. Directly across. If I look at this, since it's bicyclic, there's technically two directly acrosses. But we know that we want what type of group on our dienophile? Donating or withdrawing? Donating? Withdrawing? Cool, withdrawing. If we look, this is one directly across. This is the other directly across. Those are my options. Which is better? Top or bottom? Bottom. Why? Right. It already has the electron withdrawing group on it, and I know electron withdrawing groups on my dienophile is a good thing. So I picked that one. So I can draw my arrow directly across, just like I did over there. And I know that my arrow will point to my dienophile, which is my orange guy. Then, my bonds neighboring, touching the dienophile piece, the orange piece, are newly formed bonds, so I get rid of them. I like when everyone's head goes up and goes down. Same. Okay, so when you do this in dry erase marker, you erase the bonds, like that. Then I just redraw them nicely. So I know that my arrow points to the dienophile, so I need to make him back into a double bond, and I just keep the group on there. And I know that the red guy is the center of the diene, so his next door, he's in like the middle, so he's this guy. So I give him his bonds back, and I just count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Plus. Does that make any sense? Okay, made sense to Eddie, so that's good. So let's look at another one like that, going backwards. Let's look at it here. Let's do it here. So I have it written over here. Yeah, this is for Vincent. We get this stuff all backwards as well.
I'm at 17%.
Okay. Okay. And then my red is orange. Okay, first step. Someone tell me what the first step is. What's the first thing I circle?
Your middle.
Double bond. So this is my newly formed double bond. Then what?
Arrow.
Right, arrow directly across. Where does my arrow, what does my arrow point to? Good, dienophile. Orange. What's next to the dienophile?
Bonds.
Right, the bonds I want to get rid of. This guy and this guy. Looks really small. Okay, so I erased them. And if you redraw it in pencil, you can erase yours too. In this case, there was only one directly across, but it also still has the withdrawn bonnet, so it doesn't matter. So everyone good with that part? Circle stuff in red. Draw an arrow across. Well, you don't have to circle in red, but find the double bond. Draw an arrow across, and then that's your dienophile. The two bonds touching it were your newly formed bonds. So since they were just formed, you didn't have them originally. It should be. I mean, if there's no electron withdrawing group in the compound, then no. But like the other one we did, we had two choices. That's the one you want to do. That going forward is maybe more reactive. So then if I look at this piece, over there I had two pieces. With this guy, if we look, we have, if I look at it, it's all connected. I erased two bonds, but they're still connected. So when I draw it out, it's just going to be one big long piece. Okay? Question, Alejandro?
I just wanted to know what it looked like before you erased it, but I got it.
This looks like?
Yeah.
Yeah. And then I just erased them because I know they weren't there to start.
Yep.
And then I notice, or maybe you don't notice, but you should make sure to check that it's one big piece. So you're just going to draw it out in a big straight line. So, the other thing to check would be stereochem. So here our withdrawing group is a wedge. And we see that this hydrogen that's going to be my diene when I draw it out is dashed. So are they cis or anti? That should have been an easy question. One of them is wedged and one of them is dashed. So are they cis or anti? Anti. Okay. So when they're anti to each other, it's a what group? C. It's a C group. So that hydrogen is a C group. So I know I have the 5. The hydrogen is a C. So the other one has to be in the other one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And removable. Oh, I dropped my little one. Okay, so you can write out your numbers and rewrite it nicer.
Would it be wrong if we just left it as like
I don't think
instead of
so.
drawing it out as
No, you can leave it like that. Leave it like that. Yeah, if you could just not redraw it out straight, doesn't really matter. You can leave it.
then we wouldn't have to.
Yeah, then you wouldn't have to do that. But erase all your circles and squiggly lines. Okay. This guy? Oh, did I do him flip flop? We want him. Yep. These guys, one is wedged and one is wedged. So are they cis or anti? Cis. So I have to keep them cis. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 9, 10. I want them to be on the same side. So if he's here, I have my hydrogen here. Oh, it was right. And I want him on the same side. Does everyone see why? If they have the same stereochem, they're both wedges in this case, I want to keep them both the same direction. No problem. Okay, so that's how I do them backwards every time. Because all I have to do is draw an arrow. Once you do it a few times, you don't have to circle things in lots of colors. You just draw an arrow. So are there any questions with that? Yeah.
Yeah, on the test or something, with the H on 9, since normally when we draw those out, we sometimes don't end up writing the H, like how would they know if we put the CO2, CH3 on the right, like, position?
Because even if you don't draw it, it's still on that position. Because the methyl's that way, so the H has to be that way.
Oh,
So
okay.
even if you don't write, I just write it in so people can see it. You don't have to write it.
Okay.
Aromaticity. Done with this all day. Okay. So yeah, that's pretty much how you do the problems. It's just a matter of identifying like where to draw your arrows and everything. That wasn't. And keeping track of lots and lots and lots of stereochem. Okay, so what I'm worried about with aromaticity is that rule. So does someone want to be kindly volunteer to tell me that rule? Otherwise I will fix it. I'm still talking. I have like 2 hours to talk. Wonderful. Does anyone want to tell me the rule for aromaticity?
Equals rule or the planar?
Yeah. Who wants to tell me what it is?
First, it's got to be planar.
Okay.
It's got to have conjugated system,
Okay.
and you got to follow the 4n plus 2 thing.
The 4 and plus 2 thing. Good. Alright, so. Oh my god. Is everyone aware that when we're talking, well, like, for this class, when we're talking about aromaticity, we have aromatic, that's it. We have aromatic, non-aromatic, and anti-aromatic. It's not like aromatic and other everything else. Some people are not aware. So we have, I'm going to do this in a nice flow form. Alright, so I don't know who answered before, but it was a good answer. The 4n plus 2 rule isn't some sort of magic spell that tells you the answer to your 5-point multiple choice question. It just helps you. So if you have a compound, you don't automatically chant 4n plus 2 over it. So first thing I think you should check, this is how I do it, is whether or not it's conjugated. Alright? So we want to make sure that the double bonds can go all the way around, right? We want to make sure those pi electrons are really localized across the whole thing, around the entire ring. Okay? So it's a yes or no question. So if it's not conjugated, it's non-aromatic. Okay? If it is conjugated, we have more stuff to do. So it can either be aromatic or anti-aromatic at that point. From there, the next thing that I look for is I do the 4n plus 2 rule, and that's true. The difficult part with that is determining what number. So for here, you do 4n plus 2 equals pi electrons in your conjugated system. So don't plug in your electrons for n, because you won't get the answer right. Okay, so if n equals an integer, a whole number, it's yes or no. So if it equals a whole number, yes, so then it's aromatic. No, it's anti-aromatic. Aromatic. So if it equals like 2.5, it's still anti-aromatic. Even if it's a nice, not whole number, it's still anti-aromatic. So if you look, if we set n equal to 0, 1, 2, 3, so the first 4 integers that n can be, if we look, 0, we get 2. So that's 2 pi electrons in the system. If we plug in 1, we get 6. If we plug in 2, we should get 10. And if we plug in 3, we should get 14. So I know a lot of students are saying, like, I don't know how I explained it, but a lot of students were confused if it was like multiples of 4 or something.
Yeah.
Yeah, I don't know. I would just know that, I mean, yeah, but no. I mean, they're not multiples of 4. They're like plus 4s of each other. Is that a word? But yeah, so we really don't go past that many. I mean, I don't think I've ever done one that has more than 14 pi electrons. So if it's not 2, 6, 10, or 14, n does not equal a whole number. So it's anti-arithmetic. Does everyone see why? You can plug it in every time if you want. Go for it. But if it's not 2, 6, 10, or 14, then it's not going to be arithmetic. Yeah. So if we check if it's conjugated. If it is conjugated, we want to decide if it's aromatic or anti-aromatic. It's aromatic if when you plug in the number of pi electrons in the conjugated system, when you plug in that number here, you solve for n. If n is an integer, it's aromatic. If n is anything else, it's anti-aromatic. Even if it's a nice not integer, it's still anti-aromatic. So we really don't go above that. We don't go to that many pi electrons. So I really just think about these numbers. So if it's 2, 6, 10, or 14, if you plug those numbers in here, you get n as being an integer, as being 0, 1, 2, or 3. You can go higher, but I don't think you're going to use that many electrons. So if you don't have 2, 6, 10, or 14 pi electrons, n will not be an integer. So then you don't have to do simple math and add things to the other side and cross things off. Any other number is we really shouldn't be going high. So basically any other number is anti-aromatic. Make sense?
Yeah, I'm one of those people that go by the whole multiples of 4 thing.
Mm-hmm.
The way I look at it is, suppose you have a compound, right? And what I do is I count all the correct number of pi electrons. You know, counting the correct lone pairs and not counting the lone pairs if need be. And if I can divide it by 4, it's anti-aromatic. But if I can't divide it by 4, it's aromatic.
Okay.
But
It's just whichever way you want
Yeah.
the math out. But I don't like it.
that was like the logic behind the whole multiple thing.
Yeah, it's the same thing. You can plug it in every time if you want and literally like -2. And -2 from both sides and do it that way every single time if you want. Doesn't matter. But I don't like doing that every single time. So if it's not 2, 6, 10, or 14, it's not an integer. It's not 0. It's not the lowest integer. It's going to go through. So that saves me time. But if you want, you can always plug it in. So that's easy enough. Especially if it's not conjugated, because then you don't have to do anything. So the hard part is determining what number to plug in. Yeah.
Is there any difference between non-aromatic and anti-aromatic that we have to know about, or just how to get?
I mean, you should kind of know about it. So, the other thing, because I'm going to forget to say this otherwise. Here, do you want to tell them why? Sure, your explanation is much more complete.
Why anti-aromatic is bad?
Yeah.
Anti-aromatic refers to compounds that would, if they existed, have unpaired electrons, and that's really terrible. The way you should really think about it, the way it's drawn there is aromatic is good, anti-aromatic is bad, and non-aromatic is in the middle. So that's a good way to put it. That's the difference between non-aromatic and anti-aromatic, really. Is that anti-aromatic has factors that actively destabilize it, whereas non-aromatic, it's not a valid question to ask, because there's no conjugation sort of going on. Does that answer your question?
Yeah.
Does that answer your question?
Oh, does that answer your
Yeah,
question?
thank you.
We're good? Okay. So basically, a lot of people, they see, okay, well, non-aromatic are not conjugated, and aromatic and anti-aromatic are conjugated, so non-aromatic must be the worst. But that's not right. So I know non-aromatic are not conjugated, but anti-aromatic, like Peter said, have things like negative. So this is good, this is neutral, but this has things actively that are actively negative, hurting you. So don't get confused with, don't think they're in this order, they're in that order. So if you get a multiple choice question where they give you 3 compounds and they tell you to rank them in order of increasing stability, which I'm pretty sure has definitely been a question, figure out what's aromatic, non-aromatic, anti-aromatic, and put them in that order, the correct order, okay? So anti-aromatic are the least stable, okay? So don't get confused by this. So that should be, as long as you can figure them out, make sure you put them in the right order, okay?
And
Peter.
before-
Yeah,
By conjugated at the start of your flow chart, you should really specify cyclically conjugated,
I should.
conjugated completely in an unbroken circle.
I don't know how to specific. All right. So let's look at a picture. Let's look at an easier picture. You didn't have any questions. All right, okay, let's look at this one. Now let's go back by Woodson. Okay. So, does everyone see that's conjugated? We have double bonds alternating, okay? Still conjugated. Better, because it's even more, it's longer. Okay, so it's conjugated, it's double-wise it costs more X. Cool. Alright. Does everyone see that that's conjugated? We still have double bonds and they're still alternating. I just wrapped it in a circle. Okay? So, benzene, right? Conjugated, so we're good with that. Okay? If I did this, is it still conjugated? Yes?
Just
No? Okay. So this part of the compound is still conjugated. Because we still have double bond, single bond, double bond. Alright, so that's like this piece. Okay? But the ring, the entire ring is not conjugated. So that's I believe what Peter was mentioning here. That when I erase, is it still erased? Yeah. The ring, as I have it now, is conjugated, but the ring, the entire ring isn't conjugated. So part of it is, okay? So the entire ring has to be conjugated. So you have to have the pi electrons able to go around the whole ring, okay? So as of right now, that compound, how I have it drawn in the ring, is not cyclically conjugated, so that's non-aromatic. Once I put in that other double bond, like this, now it's conjugated across the entire ring. So then if I look, yes, how many pi electrons do I have in that system?
8.
More than 2 people should know that. 6. 6 is on my chart. So if I do 4 plus 2 equals 6, and I minus 2, and now. Alright. Does that make sense? So I got n equals what? Yeah, I got n equals 1. Got an integer. So it is aromatic. Okay? So benzene's aromatic. I hope we got that part. Alright. The other thing to check is the hybridization. So, hybridization of a carbon on a double bond is
SP2.
sp2. So, sp2, 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 sp2. Yeah? sp2, 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 sp2. All the ones touching the double bonds are going to be sp2 hybridized. So, if we look at without the double bond, sp2, 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 but these guys are
SP3.
3. Okay? So when you're checking, if not all the M's in the ring are sp2 hybridized, and you can't make them sp2 hybridized with residence, then you know that it's aromatic. So with this guy, there's no residence. I can't do anything. don't be confused. Be like, oh, I put double bond there, yay, now it's just, no. There's already 2 hydrogens here, yeah? So we can't push double bonds onto that one. So don't do that. Once I put double bond back in, sp2, sp2. Not too big. Okay? So you want all the ends of the ring to be sp2 hybridized. And we check the cyclic conjugation, and we plug it into the magic math.
Wait, Jen,
Yeah.
before, when you didn't have the bond in there, did you say it's not aromatic or non-aromatic?
It's both. It's non-aromatic. Not the entire ring isn't conjugated anymore, so then you go no, and then it's not aromatic.
Okay,
Alright?
thank you.
Okay. So we're good with cyclically conjugated. The only other problem is figuring out what to count and what not to count. But it's not that big a problem. Something like that. Is this conjugated? Is the entire ring conjugated? Cool. What do I plug into that? How many pi electrons are in the conjugated system?
6.
Good. Alright, so we know this looks pretty much, it looks like benzene, right? So we have this nice conjugated and a 6-membered ring and it's all pretty. So, some people, okay, there's a lone pair there. We don't count the lone pair in this case because we don't use it to make the system conjugated. These electrons that are already here already make it conjugated, so we don't need the lone pair. If we had something like this, is this conjugated? Oh, I look and everyone changed their answer. That's frightening. Okay. Does it look conjugated? Do we have
Looks like
alternating
it.
double bonds? We have at least a piece conjugated, right? We at least have those alternating. So what we want to look at is in this one with the nitrogen, we didn't need the lone pair to make it conjugated. It already looked conjugated, it was good to go. With the oxygen, it's kind of like, but we have 2 lone pairs. So do we use none, do we use 1, or do we use both pairs? Oh, okay. Okay. So if we want to take this and draw him out nicely, we want to take the lone pair, put him this way. We want to move the other guy away, because we have to. And we want to put this guy back. No, we want to put him back. No, I want to put him on the other. Put him here. No, put him here. Yes? Okay.
Put 10 electrons on oxygen.
Yeah, that's what I was thinking. I was like, that was like really silly. Okay. Alright. Correct. Okay. Thank you. So if we look, it went from being looking conjugated here, and now it's looking conjugated here. And if it went the other way, it would look conjugated on the other side. So you want to notice that you have the pi electrons going around the entire ring. Does everyone see why? Does everyone see pi electrons? Okay. Does everyone see that the pi electrons are moving?
Actually,
Okay, that's okay. These guys are pi, and these guys are pi, and these guys are pi. Okay? So right now they're touching those carbons. And this is just resonance, right? So I'm not reacting it with anything or anything like that. Once I move them around, these guys are pi, these guys are pi, we got pi over here. So we have the pi across the whole ring, moving around the whole ring. And if you notice, we only use 1 pair in the oxygen. So how many pi electrons are in my conjugated systems? Is 6 a magic number?
Yeah.
Is it aromatic?
Yeah.
Yes.
That's it. Okay? So the key there is don't count both pairs. Don't count both those lone pairs. And you don't use this lone pair, but sometimes you might with a nitrogen, so you have to check with each compound whether or not it's conjugated or whether or not you need it to be conjugated or not. So if you need it in your resonance to make it look conjugated, you count it in the pi system, and if you don't count it. And then if you count them and it's a magic number, it's aromatic. That's it. And then you rank them correctly if you have that multiple choice question. And you write down your paper and you do it nicely. And you get 5 points and then you're happy. Okay, let's look at chapter 15. Any questions with this aromaticity? Yeah.
So what's like an anti-aromatic thing?
Anti-aromatic would be if I had a ring and it was conjugated, but I had an extra, do I have a nice picture? If I had a conjugated ring, so the pi electrons would be localized across the entire ring, but it's not one of these magic numbers. So if you have like an 8-membered ring, that could give you really weird shaped rings. So sometimes it'll be conjugated because it's, if you draw it out, it's conjugated. But since it's a different shaped ring, like the number of electrons it uses is different. So if it's not one of these numbers, once you count it, it's anti-aromatic.